Hi everyone, my name is Aleman Castaneda and I'm going to be talking about the project that I've been working for the last 2 years. It is about super resolution microscopy that enables 3D localization of single molecule and also gives you the information of their orientation. We call it Coordinate and Height Super Resolution Imaging with Dithering and Orientation, or simply CHIDO. And this is a collaboration between Institut Fresnel at Aix-Marseille Université and Institute of Optics at the University of Rochester. Hi everyone. Let me give a brief introduction of super resolution polarization microscopy. So first of all, it's an optical technique, meaning that it has a good compromise between resolution, field of view, and penetration depths. Not only that, given the damage threshold of light, it permits in vivo experiments. This is important for biological applications. Now, using fluorescence, also super resolution can be achieved. This is done by, instead of forming a traditional image, as I'm showing in the figure A on the right, what we do is that we let each molecule emit light at its own time. We capture the PSF, and then we calculate the centroid or theta function in order to get a more finely detailed image, as I'm showing the figures C1 and C2 on the right. Not only lateral resolution is important, also in-depth position will be required. In other words, we would like to know how defocused molecules are from the in-plane for the perfect in-plane image. And there are many approaches. We are basically interested in the ones that engineer the PSF. And lastly, light has another degree of freedom, which is polarization. This is important because molecules absorb and emit light as dipoles, and this affects the polarization of the emitted light. Then, by measuring this polarization, we can actually know the orientation. Here in the figure on the left, I'm showing some actin filaments, and we're not only interested in the main direction of the filaments, but also on the structure within them. This is important to follow the growth of biological tissues. Hi everyone. As I mentioned previously, we are interested in methods that engineer the PSF such that its shape encodes either the molecule's orientation or the in-depth position. As I'm showing in the left figure in the purple rectangle, already the PSF shape changes with the molecule's orientation. Now, for the in-depth position, we use defocused. Although defocus changes the PSF, it does it in a symmetrical way, so you cannot know if you are closer or further away. There are many methods to surpass this problem. The easiest one is adding astigmatism to the system via a cylindrical lens, as I'm showing in the figure on the left in the green rectangle. You can see how as you move in depth, the PSF goes from horizontal to vertical. There are more sophisticated methods such as the double helix face mask. You can see that the 2 points rotate as you move in depth. Now the problem, as you can already see, is that the PSF grows a lot, and this can be problematic when you have a low number of photons. The problem comes when you try to do both the orientation and the in-depth position, because the deformation of the PSF is quite similar, and then it's difficult to recognize whether it's coming from the orientation or the defocus of the molecule. Hi everyone. This is where CHIDO enters the picture. What we do differently from other methods is that our phase manipulation is actually polarization dependent, meaning that in each circularly polarized component, the information is encoded, both for the localization and the orientation. This is why it's important to image separately each right and left-handed components. We do this polarization-based filtering by a birefringent mask, which is simply a window that has 3 points of stress that generates this birefringent pattern. This is called the stress engineered optics. It was invented at the University of Rochester several years ago, and it has been used for paraxial polarization measurements. I would just like to mention that CHIDO can be thought as an analog in a non-paraxial regime, since we're using really tightly focused light. Hi everyone. So what are the PSFs using CHIDO? For example, as I'm showing the first column, when the molecule is oriented horizontally, we get this moon shape. As the molecule starts rotating, the PSF rotates double the angle. So as you can see in the third column, for example, the molecule is now vertical, so it rotated 90 degrees, and the PSF correspondingly rotated 180 degrees. Now, when you have a longitudinal molecule, we get this PSF with trigonal symmetry, and when the molecule is wobbling, as in the fifth column, the PSF only gets blurred. The important thing is that it gets blurred in a known way, so we can retrieve the information of the movement. Now, just for comparison, in the first row, I'm showing the PSF of a diffraction limited system, so a system that has not been altered, and you can see that actually our PSF doesn't increase so much of size, roughly twice or thrice. And also you can notice that alone the PSF changes with the orientation of the molecule, but you can see that the signature is not as strong, and when you have noise or a lot of background, this becomes problematic. Now, you may be asking why we are imaging separately the left and right-handed polarized components, since they are giving the same shape. Now, this comes at hand when we have defocused molecules, Please pay attention in the first column. When we defocus the molecule, these PSFs counter-rotate. And so by the amount of counter-rotation, we can get the defocus of the molecules. And so we have the 3D localization. Hi everyone. We decided to use CHIDO for storm-like measurements of actin filaments to which we attach fluorophores. As I'm showing in the figure B, you can see how these cones that represent the single molecules and their wobble, they follow the main orientation of the filaments, and even in the top, how two filaments cross. These two molecules have the orthogonal directions and they are at different heights, so this is a nice result. On the right, I'm showing some experimental PSFs and the theoretical fittings. Hi everyone. With this, I hope I have convinced you that CHIDO is a great technique for super resolution polarization microscopy, since it not only enables the common traditional super resolution in the transversal position, but also it gives the information of the 3D orientation by changing the PSF shape. Also, the C localization, the in-depth localization, can be obtained by the counter-rotation of the PSFs. And lastly, the wobbling or movement of the molecule can be obtained by the blurring. Hi everyone. Some future work perspectives. We would like to improve our experimental PSFs. Also, so far, we have used only the minimization of the RMS error in order to fit our PSFs. We would like to implement other estimation methods, such as the most likelihood estimator, and why not also use the algorithms for overlapping PSFs. I would like to thank the funding. Thank you for listening. I would gladly answer all your questions, and this work has just got accepted in Nature Communications.